In this module, we're going to establish techniques to find the maximum and minimum value of a function. In other words, find its extrema. This is important because in practical problems, you often want to maximize or minimize a certain function. It might be that you want to minimize the amount of energy you use, or that you want to maximize your profit. In many cases, we are able to model these kind of problems as a so-called optimization problem. In other words, we want to find the maximum or minimum of a certain value of a certain function under certain constraints. So we will get to that, but first we need to look abstractly at how to find this minima and maxima. So what are we talking about when we are talking about the maximum or minimum value of a function? If a function is defined on an interval d, we're going to say that it has an absolute maximum on that interval d at c, where c is an element of d, right? So c has to be a point in the interval d. And in that case, the value of the function at c is going to be called the absolute maximum of f on d. And this is the case if f of c is the largest value that the function f takes on d. In other words, f of c is greater or equal to f of x for all x in d. Similarly, the absolute minimum on d of a function f is the smallest value that the function f takes on d. In other words, the function has an absolute minimum at c, where c is a point of d, if f of c is less than or equal to f of x for all x in d, in which case we call f of c the absolute minimum of f. Okay, the first observation is that this absolute maximum and minimum may or may not exist. Consider functions that are defined on the real line. So this is the interval d that we're going to consider for this example. Let's look at this picture. We have the graph of the function is a straight line, and certainly it has no maximum and no minimum on the real line because the function is decreasing on its domain and it doesn't reach any minimum or maximum. This function, also defined on the real line, would have a maximum value. Specifically, the maximum value would be 3/2 and it occurs at -1, but you see that it has no minimum. So we can have a maximum without a minimum. For this function here, we have an absolute minimum. The smallest value that the function reaches is -4 and it occurs at 2. But we have no maximum. There is no largest value that the function takes. So we can have no minimum and no maximum, or one but not the other, or we could have both. This function here has an absolute minimum. The smallest value that the function takes is -1 and it occurs at -2, and a maximum. The largest value taken by the function is 1 and it occurs at 2. Now another observation is that in the definition we talked about the absolute maximum of the function on a certain interval. So I want to point out that this choice of the domain matters. Let's take the example of the square function on the interval 0, 1. So this is what it looks like. And since we're looking at the function on the closed interval 0, 1, we include the endpoints, and the function takes a value 0 at 0 and 1 at 1. Evidently, 0 is the smallest value that the function takes on that interval, and therefore we have a minimum of 0, and that occurs at 0. And similarly, 1 is the largest value that the function takes on the interval 0, 1, so we have a maximum of 1 that occurs at 1. What if instead we were looking at the same function but on the interval 0, 1 that is closed at 0 and open at 1? Now this time the function takes a value 0 at 0, so we have again a minimum of 0 at 0. but the 0.11 is not included in the graph. Remember that we said that the value C in the definition has to be a point in D, and so there is the only potential maximum value would be 1, but the function doesn't take the value 1 on this interval 0, 1 open at 1. So there is no maximum in this case, because for any x that I pick in the interval 0, 1 open at 1, then I can find another value in that interval that is between x and 1. The value of the function at that point between x and 1 is going to be greater than the value of the function at x. In other words, I can always make the value of the function greater. So there is no maximum. With a similar argument, if I consider the function on the open interval 0, 1, then the value doesn't take the value, the function doesn't take the value 0, doesn't take the value 1, and therefore there is no minimum and no maximum. So to summarize what we have seen, the existence of an absolute minimum or an absolute maximum for a function depends, of course, on the function, but also on the domain on which we look for a minimum or a maximum. So this is not very satisfying because before we start looking for the place where the function takes a minimum or a maximum value, we'd better know if such a minimum or maximum exists. So we would like to have at least some sufficient condition to be sure that what we are looking for exists. And a sufficient condition is given by the so-called extreme value theorem. This theorem says that we are going to have an absolute maximum and an absolute minimum provided that the function is continuous and that the domain is a closed interval. So the important conditions here is that the interval D that we were talking about is a closed interval and that the function is continuous on that interval. Now in the next video we are going to look into how we find this absolute maximum and minimum provided that we know that they exist.